welcome to lecture 11. Today we will discuss about the deviations of Raoult's law. Already we have discussed about the negative deviation. Today we will discuss about the positive deviation and the applications of Raoult's law. So, let us start with the positive deviation discussion. Here what happens in case of positive deviation, the interaction between the molecule A and B is less than that between the attraction force between the molecules of the pure constituents. Here again you can see that we have plotted vapor pressure in y axis and composition in x axis, and here the dotted lines represents the vapor represents the curve which would have obtained if the system would have followed Raoult's law, and this white solid dotted lines, this represents your vapor pressure, increase in vapor pressure of the component A and of the component B when A is added and B was added to it. Now, here is the vapor pressure of B and here it represents the vapor pressure of A. So, as the amount of A goes, as the amount of A increases and it is added to B, here we can see that the vapor pressure of B, here we can see here that the vapor pressure of the B is increasing. Vapor pressure increasing means its escaping tendency increases. In the previous one, in the negative case, what we saw that the vapor pressure was decreasing. So, vapor pressure decreasing means escaping tendency decreased, but here what we saw that the vapor pressure is here the vapor pressure is increasing, that means the escaping tendency increases, and similarly here also the vapor pressure increases, that means the escaping tendency increases, and here the total vapor pressure has increased, that means the vapor pressure is increasing. Okay. So, as the vapor pressure is increasing, when this interaction between A and B, here we can say that the interaction between A and B is less than that of the interaction between AA and BB. So, we can say that it shows positive deviation, means it will not allow the allow the formation of the solution. Okay. And here this occurs due to the dissimilarity of polarities or internal pressure of the constituents, and the evaporation tendency of both A and B increases. So, the partial vapor pressure of the constituents is greater than expected in Raoult's law, and the system is said to establish positive deviation. So, it establishes positive deviation. This is the example of positive deviation. Following liquid pairs are benzene, ethyl alcohol, carbon disulfide and acetones. And what happens in this case? They have the tendency to escape, that means they will not form solutions. So, they facilitates, they occurs mainly in case of your associations, and negative deviation it is shown in mostly in the case of solvation, but this positive deviation is seen in case of associations. So, it will not facilitate the formation of solutes. Why? Because the escaping tendency increases. So, both of them try to escape from each other. So, what happens? They do not get into the solution. Now comes the application of Raoult's law. when we discussed on the application of Raoult's law, the mole fraction of either components approaches 1, then we can say that if the total mole fraction of the system is 1, and if we know the mole fraction of A, then we can find out the mole fraction of B, like B, mole fraction of B will be 1 minus mole fraction of A. Then Dalton's law. What we understand by Dalton's law? Dalton's law states that that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressure of the individual gases. Here total pressure is equal to, if we are taking n number of gases, individual gases, then the total pressure will be the summation of the partial pressure of all the individual gases. Then comes volatility. What we understand by volatility of a substance? Volatility of a substance in a liquid solution can be defined as the equilibrium partial pressure of the substance in the vapor phase, divided by the mole fraction, of that substance, that is P A divided by X A. Then what we understand by relative volatility? Relative volatility shows that volatility of A divided by volatility of B. That means we can write it in terms of mole fraction and partial pressure. Then comes it's actually when we study these all applications, the applications of Raoult's law, mainly it is important in this in industrial distillation process. It indicates how difficult or with how ease the distillation process can be carried out. Now, application of Raoult's law. When we discuss about the application of Raoult's law, what happens? Distillation of binary mixture, what happens? The relationship between the vapor pressure and the composition of the binary liquid phase is the underlying principle of distillation. For miscible liquids, we plot boiling point of the various mixtures, and what we do in this case, in place of vapor pressure, we use boiling point and composition of the binary liquid phases to plot the graph and to do distillation. And here we know that a substance which have higher vapor pressure means it is more volatile, and it means that it has a low boiling point. So, we can draw this graph, we can see the distillation of binary mixture. Mainly simple distillation takes place and fractional distillation takes place. Then we have azeotropic distillations are there, steam distillations are there. Okay. So, first is your simple distillation. In case of simple distillation, if the liquids which are used has to be separated and their boiling point is quite different. Okay. If the difference in their boiling point is more, then we go for simple distillation, and if their boiling point is almost similar, then we go for fractional distillation. Now, we will start with this graph. So, before explaining the graph, we will just go through the examples, some of the examples of the liquid mixtures which can be separated by simple distillation method. One is your methanol and water, then separation of phenol crudes into gasoline, kerosene, fuel oil and your lubricating stocks. And the observation that the vapor in equilibrium, which is when it is in equilibrium, it is found that it is richer in more volatile component, and this is expressed quantitatively as Raoult's law, as Raoult's law. Now, if we see that if a graph is plotted between your boiling point or temperature and your composition, or and which is given in terms of mole fraction, this is a boiling point diagram of an ideal binary mixture. Here we have, suppose we have two components A and B. Here we have 100% A. So, its boiling point is this. Now, higher the boiling point, lesser is its escaping tendency, because higher boiling point means low vapor pressure. Low vapor pressure means less escaping tendency. Okay. So, here the boiling point of A is denoted at this point, okay, and the boiling point of B is denoted by this point, okay, and this represents the liquid phase. This down curve represents the liquid phase, and this upper curve represents the vapor phase, and in between these two upper and lower curves, it represents your liquid plus vapor phase, liquid plus vapor phase in between this curve. Okay. And to plot this curve, what we have done, we have taken different composition of the A and B, that is different mixtures are taken with different compositions of A and B, then they are heated or boiled, okay, and then their graphs has been plotted, and it shows that a mixture of a high boiling liquid A is used here and low boiling liquid B is been used here. And you can see here, as the boiling point of B is less, that means the vapor which is obtained by distillation, the vapor which is obtained, it will be richer in B. Why? Because B is the volatile, is more volatile compared to A. So, according to Raoult's law, what we will get, the more volatile constituent will be the most or the major portion of the vapor will be constituted by the low boiling point liquid. And here this B is distilled at the boiling point or at B. Now, the composition of the vapor, here we can see that the composition of the vapor V1 is in equilibrium with the liquid at this temperature is C. Is it equilibrium at this temperature B is with equilibrium with the composition, that is C, and you can see this, that the mole fraction as we move from A towards B, the mole fraction of B here it is 1, means as we move from A towards B, the amount of or the composition of B increases, the amount of B increases. So, the vapor is therefore richer in B, then the liquid from which it was distilled. And when the vapor rises in the column and it meets with the condensed vapor, and as the rising vapor is cooled by when it come in contact with the liquids, some of the lower boiling fraction condensed, but still the vapor contains more volatile component than it had with when it has left the retort, and in the retort which is falling down, it will be having more concentration or more amount of the non volatile component, which is denoted by A here. Then in some cases what happens, two liquids starts to boil at a constant boiling point, and this mixture of two and more liquids whose proportion cannot be changed, or it cannot be changed by using simple distillation, and they behave as your azeotropes. They behave as azeotropes, and we cannot separate them by using simple distillation. Why? Because there they start boiling together with the same composition. For example, water and ethanol, it starts boiling at a same temperature of 78.17 degrees Celsius, and and that vapor which comes out, it always contains 4% of water and the rest 96% point something of your ethyl alcohol. That means whatever means how much temperature you provide, at that temperature the vapor which will be formed, it will contain water as well as ethanol. So, you cannot separate out ethanol completely, you cannot remove ethanol completely from the alcohol by using simple distillation. For these types, either we have to do azeotropic, we have to go for azeotropic distillations. And here two types of azeotropes can be there, one with minimum boiling azeotropes and one with maximum boiling azeotropes. A solution that shows greater positive deviation from Raoult's law, it forms a minimum boiling azeotropes at a specific composition. Minimum boiling azeotropes, what happens? Okay. Suppose here, if suppose if water is taken, water has a boiling point of 100, and if we are taking ethanol and it has a boiling temperature of 78.35, suppose, then they together they will form a azeotropic mixture, and they will start boiling at a temperature of 78.15 degree Celsius. That is its minimum boiling azeotrope, less than your 100 degree Celsius of water, and this is for your degree Celsius as for ethanol, okay, ethanol, if I write it here, which, okay, ethanol, and it's at this point it starts boiling together at a constant composition, that is it will contain it gives 4.03% of water and rest 96% of ethanol. Okay. Then comes, okay, if I have just written a roundup value, okay, then comes your a solution which shows negative deviation from Raoult's law, they form maximum boiling azeotropes. And what happens at a specific composition? Example is your nitric acid. Nitric acid has a boiling point of 83 degrees Celsius and water has a boiling point of 100 degrees Celsius. But when they start when they are heated together, they start boiling, forms a azeotrope mixture, and the mixture boils at 120.4 degree Celsius. So, what happens at this temperature? They start boiling together. And then comes, and this temperature is higher than the temperature of nitric acid and that of water. So, they forms maximum boiling azeotropes. Then comes your steam distillation. Basically, whatever we have discussed before the steam distillation, about distillation, that is simple distillation, fractional distillation and azeotropic distillation. Here basically we were discussing how to separate two miscible liquids. Now, in case of steam distillation, we can separate the mixture of immiscible liquids. Begins to boil when the sum of the vapor pressure is equal to the atmospheric pressure. Here what happens? Suppose we have taken water, it has a boiling point of 100 degrees Celsius, and we have taken bromobenzene and it has a boiling point of 156 point something degree Celsius. Okay. And when they are mixed together, they start, here I am writing here, they start to, when these two are mixed together, they start to boil together and means they boil at different composition, but the difference is here they boil at different composition, but at 95 degrees Celsius. That means we can separate out bromobenzene at a temperature 61 degrees Celsius lesser than that of the bromobenzene. So, this is your steam distillation. Then comes your application of Raoult's law. So, when we discuss about the application of Raoult's law, basically here we discuss about the your colligative property, colligative property. What you understand by colligative property? Colligative property means the property which is due to the number of solute molecules. It may be due to the number of molecules, number of ions, number of particles, means it depends on number. It is not depends on the nature of the particle, but number. So, colligative properties, there are 4 colligative property, and the lowering of vapor pressure can be explained by using Raoult's law. Here what happened, when we add a non-volatile solute, okay, and it is added to a volatile solvent, then the vapor above the solution is only due to the solvent, because we are using non-volatile solute. So, the vapor which we will get, it is not due to the solute. So, we are using non-volatile solute with a volatile solvent, then the vapor above the solution is solely due to the solvent, and the solute which is added, it reduces the escaping tendency of the solvent, and on the basis of Raoult's law, this R will be capital, on the basis of this Raoult's law, what will happen? The vapor pressure of a solution containing this non-volatile solute is lowered, and it is proportional to the relative number of solute molecules. If the number of solute molecule is increased, then the escaping tendency of the solvent will be reduced, and how much it will reduce? It depends on the relative number of the solute molecules. Then comes aerosols and Raoult's law. Now, in case of aerosols, what happens? Here we basically use a combination of Raoult's law and Dalton's law to calculate the vapor pressure of the propellant blend, to use the vapor pressure of the propellant blend. What we do here? Here basically we calculate the we calculate the partial pressure by using Raoult's law, as we know that if Pa stands for the partial vapor pressure, okay, it is equal to the vapor pressure of A multiplied by Na plus Nb. This is your mole fraction of A, Similarly, we can also get the partial Similarly, we can also get the partial vapor pressure of B is equal to vapor pressure of B multiplied by Nb divided by Na plus Nb. So, in this way we can obtain the partial vapor pressure of B and partial vapor pressure of A. These two are different, okay? And by using Dalton's law, we can say that the total vapor pressure will be equal to your partial pressure of A, pure component, and the partial pressure of B. So, this will be the pressure of propellant blend. So, it will help us to select the appropriate propellant blend depending on how much force or how much pressure is required to expel the drug, so that it can reach to the desired site. If I want topical, then the pressure which will be required, it will be less. If I want it to inhale and I want the drug to reach the lungs, then the pressure will be used, it will be higher. So, depending on that, we can select the propellant blends. Then before starting, before this concluding, so we should we can differentiate between now application is over. So, we can differentiate between ideal solution and non-ideal solution. So, ideal solution and non-ideal solution. What do you mean by ideal solution? The solution which follows Raoult's law, and here which do not follow Raoult's law. Okay. And then here the attraction force between the solute is equal to the attraction force between the solvent and solvent. It is equal to the attraction force between the solute and solute. Okay. And here the attraction force between the solute and solvent is never equal to the attraction force between the solute and between the solvent. Okay. And so, in this case we get two deviations, that is positive deviation and the negative deviation. Okay. And here del V mix is equal to 0 and del H mix is equal to 0. Here del V mix and del H mix is never equal to 0. Okay. So, next class we will discuss on distribution law. Thank you.